Welcome, everyone. Thank you for joining our webinar. Today, we have Reuben Budiardja from Oak Ridge Laboratories presenting on how to use OpenMP to harness GPUs for core collapse supernova simulations with GenASIS. If you have any questions during the presentation, please ask them using the Q&A feature located on your Zoom toolbar at the bottom of your screen. You will be able to see questions from other attendees, so please upvote or like the questions that interest you. This presentation is being recorded and will be posted on the OpenMP website. Look for an email tomorrow with further information and a link to the recording. Reuben?
Thank you, Izzy, for the introduction. And thank you for OpenMP ARB for giving me this opportunity to present our work. I would like to begin my talk with the science context that motivates this work. After all, I think the primary reason we have this software and hardware in HPC is so that we can do better science. So let's begin with a few basic facts about core collapse supernova. So star with more than 10 times the mass of our sun will end its life by a massive explosion known as supernova. The term core collapse applies because preceding this explosion is the collapse of its iron core. Core collapse supernova also marks the birth of most exotic states of matter known, the neutron stars and black holes. It is among the most powerful explosions in the universe, about roughly 10 to the 53 ergs of energy released as mostly neutrino, in a time scale of about 1 second in the collapse and the explosion events. Just 1% of this is electromagnetic radiation, correspond to about 10 to the 28 megatons of TNT. So that's 10 with 28 zeros. And this explosion event momentarily outshined the brightness of the host galaxy of the supernova. So core collapse supernova have been associated with production of gamma ray bursts. They produce gravitational wave signatures. We hope to be able to detect soon with the detectors such as advanced LIGO. So these events, core collapse supernova, happens about twice per century in our galaxy. So why simulate supernova? So I think there are at least two ways to answer these questions. The first one, the obvious one, the scientific or philosophical answer, if you will, is that we know that almost all elements heavier than hydrogen and helium in the universe, they are synthesized in core collapse supernova. So not only this element were cooked there, supernova explosion also dispersed them on the whole universe. So the saying that we are stardust is literally true here. The iron in our blood, the oxygen we breathe, the carbon in our body were synthesized at once in stars that have since exploded as supernova. Without core collapse supernova to produce and disperse these elements in nature, life as we know it would not exist. So at the end of the day, this relates to the grand scale questions of where did we come from. To understand the universe and our place require understanding of phenomena on all scales, from the larger scale, such as the structure of the universe, to the smaller scales of galaxy cluster, to the element production in stars. And this is where our research in core collapse supernova contributes. Therefore, understanding the mechanism of core collapse supernova is one way to answer the questions on our origin and place in the universe. There's also a more practical, computationally interesting and challenging answer to why simulate supernova. And for that, I start with the basic story of how a star goes supernova. So this is a reconstructed timeline of supernova 1987A, which is the closest supernova observed in modern astronomy time. For months, it was observed to have the brightness of 100 million stars, 100 million suns. So star burns hydrogen, the lightest element, into helium most of their existence. For massive star, temperature and density are sufficiently high that burning continue through helium, oxygen, neon, magnesium, all the way to iron. So at the end of its life, a massive star will have iron at its center, with layers of previously burned material like onions. So you cannot extract more energy from burning iron. So the burning stops, and thus there is no more pressure that support from the nuclear reaction to counteract the self-gravitational attraction of the star. So at some point, the core then starts to collapse on itself, followed by the outer layer. So the collapse continues until the star reaches nuclear density, approximately 10 to the 14 gram per centimeter cube. At this extreme density, the core cannot be compressed anymore. Just like if you try to compress a tennis ball, at some point you cannot compress it anymore because of the strong nuclear force. So the collapse suddenly halts the core bonds, generating shock wave that propagate outside while the outer layer is still falling inward. So this high-level explanation sounds compelling to understand the explosion mechanism of supernova. This would require high-fidelity simulation to simulate. So, but what we know now, actually, when the shock starts to propagate outward, the shock stalls, and then the questions become what energized the shock to actually produce the supernova explosions that we observe. So as I mentioned, understanding the detailed mechanism requires high fidelity simulation. So just from the basic description of the supernova events, we can start to glimpse all of the complexity and sophistication required to simulate such events. Just to simulate the collapse, we need a fluid with self-gravity, a realistic equation of state that relates the fluid density with pressure and temperature, and star, of course, have magnetic field. And during the collapse, the density increased by 6 order of magnitude. This translates to at least 100 changes in length scale. So a realistic simulation will have to be able to resolve 1 kilometer in terms of length scale, while the domain size in the order of 1,000 of kilometers. So this is a multi-scale problem. Another problem or another example of the multi-scale issue is the turbulent cascade that happens in the star supernova shock, as pictured here. This is a visualization from our earlier simulation, where the cascade, the small scale, produce turbulence that have to be resolved. So this to aspect the software integration and the compute power requirements that basically produce challenging computational aspect that continue to push the boundaries of computational hardware and software. So why simulate supernova? Because this experience in trying to even simulate supernova really becomes important in our increasing understanding of complexity of software and hardware in HPC. So how to blow up a star? It turns out to be not as easy as you would think. So the tool that we're using in our research is called GenASIS. It stands for General Astrophysics Simulation Systems. Earlier version of GenASIS we have used to study fluid instability in supernova dynamics, and we discover exponential magnetic field amplification in progenitor star. So GenASIS is written mostly in modern Fortran. It is designed to be a modular object-oriented design with extensible, and we use OpenMP for threading both on CPU and in recent work for offloading on GPU. This is the high-level structure of GenASIS. At the very high level, the code has 3 major subdivisions. We call it physics, mathematics, and basics. In basics, we have module and classes for utilitarian infrastructures, including data management, I/O unit, and as we shall see later, our way to manage devices, to manage GPUs and interaction between GPU and the host. And we also have our own MPI facades to make programming a little bit easier. In mathematics, we have our manifolds, our meshes. This is a Cartesian and curvilinear meshes. We have all of the solver expressed in abstraction in mathematical way. This includes the time-dependent ODEs, partial differential equation, and elliptic solvers. And then in physics, this is where we have the instantiation of the kind of fluid type and equation of state, the type of stress energy tensor, and the kind of space type we're dealing with expressed in physics. So this layering or abstraction basically enable us to work or to implement code in extensible manners, where solver in mathematics does not necessarily need to know all the physical details of the fluid type and equation of states and that sort of things. We do somewhat unit test development for GenASIS. So as you can see here on the right side is the module is where we do all of the classes and solver, and on the left side we have programs and application example and unit test. In example and unit test we have a corresponding division to the modules that we have. So for example, the example in physics here utilize all the module in physics, and the example in basics we will touch on later only utilize classes in basics. Similarly with unit test, where the basics, mathematics, and physics correspondingly test the modules. Application is where we then write our full application for a simulation that utilize all of the modules that we have. So at the heart of GenASIS, we have this storage functionality called storage form. This is a class for data and metadata, and where metadata can include units and variable names that we use for our I/O and visualization. So we use storage form to group together a set of related physical variable, for example, a fluid variable. Everything in GenASIS, all of our solver is written utilizing this storage form. So this lets us to render more generic and simplified code and standardized storage solution for I/O, for ghost exchange, for prolongation and restriction, and that sort of thing. So the data in storage form is just a rank 2 array, a 2-dimensional array. For we call it value. Typically, the first dimension would be the number of cells and or index to the cells, and the second dimension would be the physical variables of the storage. So for example, here the storage form would store fluid quantities, where the first index represent the particular value on that particular cells, and the second index represent the quantity such as pressure, density, velocity, etc., etc. So we have methods in this storage form to initialize, which basically means to allocate data on the host, and we have methods to allocate device, and I will talk in detail about this later. This is basically to allocate and associate data on GPU, and also we have a method to update device or update host, and this deals with transferring data to and from GPU. Okay, so here's an example when we call the initialize method. In this case, we just give a shape of 6 and 6. That means 6 cells, and you can see here 6 cells and 6 variable: pressure, density, energy, and the 3 velocity, for example. We call this method, it's initialize the memory on the CPU. And then when we call allocate device, it's also initialize memory on GPU with similar size. Now here there one important point. So there are actually 2 ways to associate the host and the device memory. And in OpenMP parlance, this is called the mapping. So we can do mapping for each variable independently, and that way we create n variables mapping, or we can map the whole contiguous block, so just one mapping. So which mapping to use really depends on how a kernel is written. So here's a call with allocate device with this option associate variables equal true, which is the default in our case. So in this case, we allocate the memory on GPU, and then we create multiple mapping where each column on the CPU correspond to each column on the GPU. And this bit of code really does what I just described above. So allocate device would be called to allocate the memory on GPU. CF pointer is a call in Fortran to basically dereference this pointer. In this case, would be the GPU pointer to the scratch variable, and this is the shape of the array of the scratch array variable. And in this, we iterate over the variable, this column. We find the location in the GPU or the GPU address of each of this column, and then we make the association between this address to that address and the address on the CPU to that address. So this is the OpenMP mapping basically. And as you shall see later, associate host is really just our interface for OpenMP mapping. So this bits of code basically tells OpenMP the data location on GPU, and further on when we write the kernel, this avoid implicit allocation and avoid data transfer, implicit data transfer that we don't want. Here's the second way to associate variable. So in this case, we set associate variable equal false, and in this case, we just associate the whole block. So it's really just the head address of this host device memory is associated with the head address of this host memory. So again, this also similar as before, this mapping tells OpenMP the location on GPU. So one can go back and forth between the two ways of mapping. So we set up a method called reassociate host, and you can set the variables to be true or false to go back and forth between these two ways of mapping. So we write our own Fortran wrappers to OpenMP APIs. This is primarily because in OpenMP 4.5, some of this runtime library APIs for memory routine is only provided for C binding. And we have created our own wrapper. So allocate device you've seen before is basically an interface to OMP target alloc. Associate host is just our interface to associate pointer, OMP target associate pointer, which basically explicitly tells you how the mapping is done. And update device and update host is our wrapper to OMP target memcopy. And reassociate host is really you deassociate the pointer and then you associate it in a different way. Here's an example on how we offload computational kernel. So this is the caller on this box. First, we initialize with the number of cells and variable. We call allocate device. This allocate device allocate the memory on the device and do the association. And then we update the value with the value from the host. And then we call this kernel with this argument 3 different columns. This is the kernel. Granted, this is a really simple kernel just for illustration. But the point to be made here is that this allocate device makes the persistent allocation and association. When we call the kernel, we don't have explicit mapping. We don't need explicit mapping. It's been done here. And there's also no implicit mapping nor implicit data transfer because it's been done here. So this affirmative control of how we move and map data is really what's giving us the performance to do our kernel offloading. Here's a second example. In this example here, we set the associate host with associate variable option equal false. In this case, we just associate the whole block. Now, if you look at the different here, now we call the kernel, inside the kernel, the variable is addressed as the original two-dimensional array, so, or rank 2 array. So OpenMP see this as a two-dimensional array, and because this whole block is associated correctly with this whole block on the device, then the association works out. So, and to compare this with previous example, if you address it as a one-dimensional array, if you give it to the kernel as a one-dimensional array, then the association has to be done correctly also as the column-wise association. So it is worth noting the degree of flexibility available in mapping the host variables to the device variables. In our solver, some of our kernels requires knowledge of the spatial relationship in data, in particular, for example, nearest neighbor relationship of stencil. So the stencil relationship can often be easily represented using appropriate indexing of a rank 3 array, right? So in this case, in our storage form, we basically just kind of serialize all of our 3D mesh into 1D arrays, but using a feature called pointer remapping in Fortran, you can also address or access this 1D array using a 3D array. So in this case, for example, I'm addressing this first index with a 3D array using a pointer remapping, where the extra -1 and 0 and the +2 here represent our ghost cells. So V now is a 3D representation of this 1D array F value. So this also, it turns out this also works nicely with the way we map a variable in OpenMP. So this kernel is addressing this variable F value as 3D arrays, but the mapping still also works out as previously done, where F value is just mapping column-wise on OpenMP. So again, the nice thing here is that we don't need extra mapping clause, and only the change to the code is that adding this OMP target themes distribute parallel do, and this pointer remapping feature works transparently with OpenMP. Here's another example that's slightly more complicated. In this case, we have 4 variables. The variable S and Fi, or flux inner, is basically a rank 2 variable, and these 2 variables we call the associate host with false. So this is associated as a whole block, as a 2D block in OpenMP, while the variable A and V, A and I, and A sub I and V here is basically a rank 1 variable. Again, this is using pointer remapping. This is addressed as a 3D array on the first dimension, and on the second dimension, it's mapped the same way. So OpenMP also lets you do this with the correct mapping. So this, we only need to change the mapping of this 2 variable, and this A sub I and V use the column-wise mapping. So here's an example of the kernel where we basically mix 2 different mapping, and this also works transparently. Okay, so we basically have applied these techniques throughout our code GenASIS, but when we first started this, we work on an example that used only the basics classes, and it turns out it's still useful to keep coming back to this basic example, which only use kind of the basics classes without the complication of the higher level solver in our code, and for testing and for experimentation. So we implement a Riemann problem with only a handful of kernels. A Riemann problem is basically a benchmark problem in hydrodynamic solver. This is the similar solver is used in explicit part of our radiation transport. So this has become our workhorse kind of proxy application within our own code for experimentation and testing. And since there's only a handful of kernels, we have also ported this problem to CUDA and HEAP. Basically, our motivation is to see whether we get a parity of performance using OpenMP compare if the code would have been written with CUDA or HEAP. So here's the initial condition of Riemann problem, where at the initial there's a high pressure, high density on the left side, and then when the simulation starts, there's a shock wave because of the discontinuity start to propagate to the right. And here's a simulation or a visualization of a 3D version of this Riemann problem. This is done using about 2 billion cells using 125 GPUs when we first started our porting, just to see if we can do this and how everything works correctly. The left and right here is just a different volume plot, and the top and bottom is just a different perspective of the same box. So we also measure our scaling and speed up from using 7 threads on CPU and a GPU. This is done on our machine Summit at the Oak Ridge Leadership Computing facilities. And we obtain about 15x speed up from 7 CPU threads when we use GPU with Riemann problem with OpenMP offload. So in this plot, again, as I mentioned before, we also ported this code or this Riemann problem with only a handful of kernel to CUDA and HEAP to see if we can achieve some kind of performance parity with OpenMP, and the result is really encouraging. So this is a result on Summit with NVIDIA V100 and on Spark, which is our development machines with AMD MI100. On Summit, this was done with the IBM XL compiler and NVCC compiler for CUDA. And on Spark, this was done with the Cray compiling environment, so Cray compiler and a ROCm compiler on HEAP. As you can see in most of our kernel, OpenMP is really competitive with CUDA and HEAP, except for about this 3 kernel. And this is something that we aspire to work with our vendor partner to investigate whether better optimization or particular thing can be done for this particular kernels where OpenMP has opportunity to improve. So you also see here there's a data movement between host to device and device to host. In our more recent version, actually, this is done so that we can do MPI communication on the host, but we can also now do MPI communication directly on device with GPU-aware MPI. So we also have a version where this has been removed, so there is no more data transfer needed when we use MPI on GPU directly. And really the difference between the 2 machines here is just hardware characteristic, that for Summit there's a better link between the CPU and GPU memory. So the ongoing work that we currently have is to use meta directive as they become implemented and become available on more recent compiler. So on the left here, this is how we write our code right now. We have an if use device where if this is true, we basically run this kernel on the GPU with the appropriate OpenMP directive. Otherwise, we use the OpenMP threading directive to run this on the CPU. But really, the major issue here is that the kernel code are actually duplicated. So this is to force the compiler generate code for both device and host. So we have use case where, for example, we want to use host and device on the same solver. For example, we want to evolve fluid on the host and radiation on GPU with some kind of load balancing, and this is the load balancing is done at runtime. So whether or not you actually run a particular solver on the device has to be decided at runtime, and this is addressed by meta directive in OpenMP 5.1, where it introduced the user selector with dynamic condition. So in this meta directive, we can do something like where user condition use device, then you do target themes distribute parallel do, otherwise you just use parallel do. So this is, again, this is in 5.1, and support for this is just right now coming in with compilers, and this is something that we continue to test and work with our compiler partners to test these features. So this will be avoiding the kernel duplication that's currently happening in our code on the left. As I mentioned earlier, we have multiple Fortran and C compatibility interface because some of the OpenMP 4.5 runtime library routine only available in C binding. We aspire to replace this when it becomes available in Fortran only, in Fortran with OpenMP 5. And also we when we need to use the pin memory, we have to resort to the underlying CUDA or heap call to allocate the pin memory. There's a feature now with OpenMP 5 allocator and allocate directive where you can do this. An even better one would be to have a predefined allocator, and this is actually implemented as an extension in some compiler where a predefined allocator for pin memory can be available. So this is currently not part of the standard of OpenMP, but a better consensus and standardization would be helpful to application developer to use a predefined allocator for pin memory. So we continue working with optimization. We have observed that some scheduling policy work better for different compilers. As you know, there's a static, guided, auto, runtime. Which one works best can be compiler dependent. And so what is the best way to actually address this is something that we continue working on. And different compiler also maps to hardware differently. How TIMS, parallel do, and SIMD, for example, map to the underlying GPU hardware can be different for different compilers. So this is issue that we continue to test. And another thing that we continue to test is whether it's better for certain kernel to have more work and per target region. So one target, one offload with more work, or we can split up to multiple concurrent target launch with no weight. And again, this can be compiler dependent, can be kernel dependent, and can be hardware dependent. And that's something that we continue to work on. With the allocate directive, we can also now start being more explicit in exploiting GPU shared memory. And that's something we currently looking at in some of our kernel. So I want to tie this back with our next plan for the science work that we're doing. This is a visualization of an ensemble simulation we did earlier to investigate the role of convection and fluid instability in driving supernova explosion. In this simulation, we use a parameterized light bulb model for neutrino heating and cooling. The sloshing motion you see now is basically a characteristic of a well-known instability called the standing accretion shock instability. And in this particular case, as you shall see soon, that the model explode, and you can see this by the increasing shock radius that will be start happening now, that eventually hit the computational wall at the end of the simulation. So here you should you start seeing the shock expand and getting larger and larger, and when it start to hit the wall, then we stop the simulation. So what we found, however, is that there is certain stochasticity to the model. This is the plot of radius of the shock versus time of the same model of the sets of simulation that has exactly the same initial condition and the same neutrino hitting, except that there's a small, less than 1% random perturbation in the initial condition. So what we found out is that out of 10 simulation here, only 4 produce explosion. So this is a discovery, is that there's a stochastic behavior in the model driven by this accretion shock instability. So now that we have OpenMP offload in our code to exploit GPU, we have the computational capability to actually perform a similar ensemble simulation with much more realistic setup, including radiation transport. So our goal is to actually bridging the gap of the 2 traditional class in core collapse supernova simulation. Typically, a simulation on either have only a handful of cutting-edge sophistication simulation, or a large ensemble but simplified phenomenological simulation. Well, we have seen from our previous work that have only a handful of simulation is probably not enough to test out this stochasticity that can be part of the model. So our goal is to bridge these gaps by doing a broad survey with better sophistication, and then we have a more targeted scrutiny of selected region with increasing sophistication. So I will stop here and thank you for attending this webinar and your attention, and I would be happy to entertain any questions. Okay, thank you. So the first questions, what would be the effect if you did not have Fortran pointer remapping? So really the pointer remapping is just to make it easier for us to address nearest neighbor. Without the pointer remapping, then it would be slightly more complicated in terms of just writing the code to address nearest neighbor, but it can be done. And yeah, it's just basically it's easier to the programmer once you set up the pointer remapping. Really, you have a 3-dimensional mesh and a 3D array, and in the x dimension, your nearest neighbor will be x minus 1 and x plus 1, and in the y dimension, your nearest neighbor will be y plus 1 and y minus 1, and similarly for the c dimension. If you don't have the remapping, then you have to work out all of this indexing in a 1D string. So it's really just a convenient feature for people like us who are accustomed in seeing in our mind's eye the 3D grid. So, and the second questions, can you talk about access to your code? Yes. So I think I put it in one of my slides. GenASIS, github.com/GenASIS have the code that I just explained here, and the master brands have the all the you should be able to reproduce the work that we have that I've presented here, and we also have a paper that have more explanation or more description similar to what I've presented here. that help you reproduce the work here. And we are doing a development of more physics in our local Git repository. And typically the way we do it as we publish a paper with our work, we also push and merge to master the new development. But everything that's presented here is available on GitHub.
Okay. Looks like that's it for questions. Reuben, thank you so much for your time today. And thank you to all of you who've joined. Just a reminder, a recording of this presentation will be available along with the slides at the OpenMP website. Watch for a follow-up email that'll come directly from Zoom with a link to that recording. And as you leave the webinar, please take a moment to fill out the survey that pops up. Be sure to let us know what other OpenMP related topics you'd be interested in. Your feedback is so important to us so we can continue to share the best content with our OpenMP community. Hope everyone has a great day. Thanks for joining. Thank you, Reuben.
Thank you.